Okay, so yesterday we were doing integrals. I don't know what you would like to do today. I noticed I just looked at WebAssign, and we can look at that a moment, maybe. I think WebAssign will be on your page now. And this is the series or the sequences section in WebAssign, but I thought maybe you might be interested in what I look at. I have a thing over here which will show me all of your stuff you're doing or not doing. And I'm hoping I'm not going to miss anybody today. I'm going to keep watching today. Yesterday, as you know, one person I didn't see, and I don't care about the names here, but we have somebody else coming. Anyway, what you see here, and as I say, I don't care about where we are in the group, but this is chapter 10, section 1, section 2, section 3. The ND, the NS means somebody opened it, but they didn't look at it or didn't do any problems. The ND means they haven't opened it. So this individual has not opened section 10.2 in WebAssign. They did take a sneak at 10.1 and decided, well, this is not for me today. If you'll notice, this individual, whoever this is, has 62 points out of that, and so forth. This individual, whoever that is doing lots of homework, whereas this individual right above is doing some. This individual doesn't wish to pass, perhaps, because notice they're not doing anything. And if I slide this over and look at chapter 11, what you'll see, what we hope to see, is a lot of numbers. What I see is a lot of NDs, meaning a lot of you haven't touched this. Now, there's some evidence of some work in section 1. You'll see some people are doing stuff. I don't know why you guys aren't. Nobody's explaining to me why you're not doing stuff. But we have a test out there, and I highly suggest that these things will help you. And secondly, each of these is worth 2 points, and some of you are throwing away good grades by not doing homework. I don't know how often I can say it or how mean I can sound. My wife said I was mean earlier today when I was talking to somebody on the telephone, but that's because they made me wait for 10 minutes before they talked to me, and I wasn't very happy about that. And that poor individual probably will never know how sweet and wonderful a person I am. Anyway, some of you guys may not know either, but if I look at this individual, whoever it is, has done nothing in chapter 11. And that's too bad. It makes my job easier if I don't have to worry about you and just say, no, sorry, no good. Anyway, we get back to chapter 7 and chapter 6 and stuff. You'll see more numbers because people are doing more. Don't want to dwell on it, but I don't know how many times I can warn you guys, you need to do homework. So, and if there's reasons why you can't, nobody's talking to me. So if I go to section 1, and maybe this is the wrong thing to do because it'll give me, so what I got to do here is figure out a way to get over here without showing names. I'm not sure I can do that very easily. Let's see, maybe I can do it this way. Because I really don't care who we're talking about. I just care what you're doing. So one thing I thought we could do today is look at section 11.1, which is the sequences. And let's see if we're out of that already. Yes, okay. So now I can show you more screen legally. So we go to section 11.1. That's on sequences. And that's where I was when I started this. Just 1 second, let me get it a little bit better. Okay, these are all the problems. I'm going to expand it. And what you have before it comes up, you have a couple of videos to watch. You have 3 exercise examples that you can go through that are in the book, but they take them over here and sort of have you answer stuff. And so now they're bringing up the videos now, opening them up. But I thought we might go to problem 20 because most of the problems before that are pretty simple. This is simple too, but it may cause you more trouble. Well, let's go to 13 first. If I look at this sequence, now the answer is here, but you're supposed to ignore the answer. If I look at the sequence, this is not a series, okay? The series is a sequence also, but it's a sequence of partial sums. When we're just doing sequences, there's no ratio test, there's no comparison test, and so on. For sequences, all those tests that we talked about, integral tests and so on, those are for series. Some of them are for a series of positive terms only. Some of them are a series of absolute values. Anyway, they're different, but the sequence stuff, because you spend most of your time studying series in chapter 11, you forget about good old sequences. All we have to do with sequences is see whether they converge or not. And if I look at something like this, I see a quotient, and I need to play with this like, I'm looking to see if anybody's waiting to get in. I don't see anybody. Just a second, let me get that up so I can monitor that today. I look at this, I see a top is n square, I see a bottom is n square. Now, the way to handle this is to divide numerator and denominator by n square. When you do that, you'll have 3 over n square here. That's going to go to 0. You'll have 7 over here because that's going to go to 7 because you'll divide out the n square. You divide the n square here, that's 1 over n. That's going to go to 0. And 2 n square over n square, that's going to go to 2 because it is 2. So in the end, the limit is 7 over 2, which of course you could sneak and peek and see it down here. But part of the idea about sequences, they're a lot of times pretty easy, but don't confuse them with series. Now, in case you didn't catch any of that, this particular number 15 is a walk your way through it to see how to do it. So they show you how to do what I just said in case you weren't listening or can't hear very well. So then they give us another one here. Now, this one, the numerator is higher power than the denominator. That's always means divergence. Okay, and that's why he says do n and d and e down here. Okay, we get to some different kinds of stuff. Now, this, I write the e as the exponential function. The exponential function is a continuous function. So the limit of the exponential of something is the exponential of the limit of something. In other words, you can take the limit inside here. Now, it doesn't mean put the limit up high. This is just a symbolic definition, but it's the exponential function of. You can put that in here. So all I need to do is find out where the exponent goes. And as n goes to infinity, the exponent goes to 0. So the e to that goes to e to the 0, which is 1, which is why you see 1 right here. Now, next problem. I see this. This is not n square over n square, but it's like that. Because this time I will divide numerator and denominator by the whole numerator. So the numerator becomes 1. The denominator becomes 1 over 3 to the n, which goes to 0, and 8 over 3 to the n, which goes to infinity. So the denominator goes to infinity when the numerator is 1. That means you're going to 0. So here's 0. So when the denominator goes to infinity, but the numerator is constant, that's 0. Now, Here, the numerator is n squared. The denominator is sort of like n to the 3 halves. You can, for n large, you can kind of forget this 3n over here and treat this like n squared over n to the 3 halves. If I had that and I simplify, I'd have n to the 1/2 in the numerator, which goes to infinity, so this diverges. So anyway, I highly recommend you go in and do these problems. They will help you. I'm not done, but I don't know how many just to work through because I don't know if it means anything to you when I'm doing it this way. I hope it does. I hope you can follow what I'm saying. If you have something like this, what you have to do is write this out. And what's going to happen when you write this out, the numerator has 2 less terms than the denominator. So you cancel all the like stuff, which means you cancel everything in the numerator. And what you're left with is 2 things in the denominator. Both of those things are going to go to infinity. So this goes to 1 over infinity, which is 0. Now, that is different from this one. Please remember the rules for logarithm. The logarithm of a quotient, which this is not. This is the quotient of logarithms, not the logarithm of a quotient. So the rule is about the logarithm of a quotient. This is not it. There is no such rule for this, period. So don't cancel anything. Certainly don't cancel the LNs. That'd be kind of silly. And don't cancel the N's. So what do we do with this? I don't know. I really do know. But you have to think about this for a little while. Well, write it as log of 2 plus log n, and log of, in this case, 6 plus log n. I say in this case because you know these numbers will be different for your program in your computer than mine. But I rewrite this as the sum of 2 things over the sum of 2 things, and then you divide by log n. And when you do that, you'll get the log of 2 over the log of n, which goes to 0, and you'll get 1 for the second thing. In the denominator, you'll get the log of 6 over the log of n, which goes to 0, plus the log of n over log of n, which is 1. So this is going to go to 1 over 1, but you have to write the numerator and denominator out as sums before you can do that. This one, you do change it to x's and do L'Hopital's rule. This one, oh, great. There is a rule for logarithm. I can write this as the log of the quotient. The log of n plus 2 over n is the log of 1 plus 2 over n. 1 plus 2 over n goes to 1, and the log's continuous, so the limit of the log is the log of the limit, and it's the log of 1, which is 0, which is why you have 0 here. What do I do with something like this? I don't know how to deal with this, but now there is a comparison. It's not the comparison test for series, but cosine is always less than 1. Cosine squared is always greater than or equal to 0. So I can replace this thing by 1. And so if I call the new thing 1 over 2 to the n, call that b sub n, a sub n is less than b sub n, and b sub n goes to 0, because 1 over 2 to the n goes to 0. So we have what's called a squeeze theorem. So if the terms are smaller than some other terms that go to 0, we can squeeze, and so the limit should be 0. So I'm real happy that this limit is 0, and so on. Now, some of them get a little harder. I think I'll leave this one for you to look at. This is not hard, but it kind of looks bad. And we have some other things. What would I do with this? With this, when I look at it, I see sine x over x. So I would change the 2 over n to x, and then I'd have sine x over x, and as x goes to 0, sine x over x goes to 1. Well, when x goes to 0 is when n goes to infinity, so the limit as n goes to infinity of this is 1, which is why you have this. So anyway, in a half hour or so, you can whip your way through these problems. Doesn't have to take you 10 years. And by the way, all you're really after is getting 100 points, and we can do that in a very short time. I'm kind of joking now but some of these earlier ones are easy. Like you got 3 choices on this video, and most of us in 3 choices, if we guess wrong the first time, by the 3rd choice, hopefully you'll guess right, because hopefully it'll occur to you not to guess the same one twice that you got wrong. And so that's 2 points for you quickly. Now you're down to 98. You can look up the examples. Look, this is 5 points, and it's an example of the book. It's 2 points here. And this next example is 6 points. So we just knocked ourselves down to needing to do about 80. And I did about 20 of them for you. So basically, this is not too hard an assignment, but you need to do the limits of sequences. Okay. Now I'm going to stop, and because I don't know if any of this has been worth anything to you or not. Do you want to talk more about WebAssign? I have other things to do today. Do you want to do something else? Do you want to talk about integrals? What do you like to do? Anything? Well, nobody has a preference.
I could look at some more of this chapter 11 homework.
Okay. In the series end?
Yes.
Okay, well, let's try to look at that, see what we got. So I'm going to get out of the sequence. Wait a minute. I don't want to get off of this. I'm sure I want to send a form again. No, why would I want to do that? I want to go to home. Hello, home. Okay, so 11.2. We can do 11 anything. I just 11.2 here. Well, I got to expand this again and see what we got. I'll notice in this case, I've got 2 videos again. That's 2 points for you. Once you look at the videos, you don't even have to look at the videos. You have 3 choices for 2 answers. But let's look at this. This says AR to the I minus 1. So this is a geometric series. Converges to the limit of A to that, it says, and it says false. Well, but that is the formula. This goes to A over 1 minus R. It is the limit, but why would he say false? And the answer is that the R has to be less than 1 in absolute value. You're not told what R is here, and therefore you have to say false. This next video wants to know if a series converges, do the terms go to 0? And the answer is, he says false. But see, I just read it wrong. I said if the series converges, then the terms go to 0. That is true. What is here is the converse of that true statement. If the terms go to 0, the series converges. The answer is no. Example, harmonic series. If you sum 1 over n from 1 to infinity, that diverges, but the terms 1 over n go to 0. So when I saw this, I read it if then that way, but actually the if is over here. So this is then if, and that's false. Anyway, think about that. And you have a couple of examples here. Find the sum, and they tell you something here. They tell you it's geometric. They won't always tell you that. And when I look at it, it's geometric, it's alternating. What I need to do is define the general term and the And that means the A and the R because they're telling me it's geometric. So I look at this, 2, 4, 8, 16, 3, 9, 27. Sooner or later, I recognize these are doubling in numerator. That's one way to put it. Or another way to put it, it's powers of 2. So this is 2 to the 1, this is 2 squared, this is 2 cubed, this is 2 to the 4th. This is 3 to the 1, 3 squared. So these are off 1. So if I look at the nth term, it'll be 2 to the n over 3 to the n minus 1. And he says the A is 2. Now, how does he know that? Well, you don't yet, except remember what I just said is 2 to the n over 3 to the n minus 1. That means I got an extra 2 in the numerator. So if I would factor the 2 out of the numerator, take the 2 out of all these, I'd have 2, and I'd have 1 minus, and so on. Then the power would match, okay? Because this would become 2 to the 1 over 3 to the 1. This would be 2 to the 2 over 3 to the 2, and so on. So it looks to me like 2/3 is the ratio, except it's minus 2/3. So that's why the answer here. And he tells you the first term is 2. So now I know those two things. I know the formula. It's A over 1 minus R, 2 over 1 minus 2/3. That's 2 over 1 plus 2/3. That's 2 over 5/3. That's 6 over 5. That's why the answer. So in section 11.2, you're going to have some geometric series. You're also going to have, these are examples, harmonic series, and you're supposed to know by now it's divergent. And here's the reason why it's divergent. These things get bigger and bigger if you look at them. The first 4 terms is bigger than 1. The first 8 terms is bigger than 1.5. The first 16 terms is bigger than 2, and so on. So it diverges. And there's some calculate sum of the series whose partial sums are given. So if I'm given the partial sum, what is the sum of the series? It's the limit of the sequence. So here's a sequence to take a limit. I'm really happy that we did the first section because now we can deal with the sequence. What's the limit of this? Well, it's n, 4 is 4, 7 is 7. The n is right there. And this is 0.9. Now, in 11.1, there was a example that said if the r is less than 1, the sequence converges. So this is going to converge, and this part goes to 0. So the sequence of partial sums goes to 4. So that's the sum of the series. Don't have to know what these terms are. Goes to 4 because they're telling me about the sequence. Okay. And then you have some games here about just filling in the terms. Calculate the first 8 terms of the sequence. That's just to fill in 2 over, put in 1, 2 over 2, 2 over 3, and so on. And because they insist that you have to consider decimals, which I think is stupid. Anyway, why do this? It really isn't stupid. I just don't like to play with decimals so much. The question is, do you think the series of terms is going to converge? Okay. Well, by the way, these aren't the terms. These are the sums of the first. So when I read this better, calculate the first 8 terms of the sequence of partial sums. So don't just stick 1 in here and say 2, although that's true, because that's the first sum. But the second sum, if I stuck 2 in here, well, maybe we don't know what it is. What they're doing is adding the first and the two numbers. So when I look at these partial sums, they're getting big. This is going to be a divergent series because the sums are going to infinity. Now, we have in the chapter a divergence test for series, which says if the series terms don't go to 0, then you have divergence. Now, in this case, the terms do go to 0, so that doesn't tell you anything. But the partial sums look like the limit is infinity. That's why you know it's divergence. If the terms themselves were going to something besides 0, then you could also say it's divergent, but you can't do that for this problem. What about this? Well, this one is an alternating series. When does an alternating series converge? All the things without the -1 have to do, which is 1 over n factorial, is go to 0. And 1 over n factorial certainly goes to 0. Now, I'm just looking at the problem about convergence. The author wants you to write down the first partial sums. And do you think this is convergence? Always wanting you to do here is see what you think. Well, this is 1, the next sum is this, next sum is this. Do these seem to approach some number? And what you're supposed to see is they seem to be approaching some number. So from the numbers you get here, you think it converges. But I know it converges because I know the alternating series test. That's because we've had the chapter already. So again, first partial sums, this is alternating again. Don't be confused. It's minuses there, but it's really -1 to the n. And if you look, these things seem to go to something. These numbers are all close to 4. Here we even have a picture of what's happening. So some of this you can take time and look at because it's good for you to look at different ways. Now, you get to number 13 here, he talks about it is geometric. So that tells you something. So what do you have to identify? The A and the R. Now, why did he say in the previous thing the A was 2? Well, if this is geometric and you know, the first term is always going to be A. So the first term is A, that's 3. The R, well, I don't know about the R. It looks like 8 square, 8 cubed. You may not know 8, this is 8 cubed, but that's 2 to the 6th power, 2 to the 8th power, and that's 512. What's happening in the denominator? You're getting some powers here. Why does he think it diverges? Well, if the common ratio is more than 1, it's going to diverge. When you go from this term to the next term, what are you doing? You're multiplying by 8 in the numerator and you're multiplying by 3 in the denominator. That's multiplying by 8/3. The common ratio is -8 over 3, which is bigger than 1. So this geometric series is going to diverge. So anyway, this is the first so many. Let's go toward the end. See what's down here at the bottom. Some nice problems, actually. Okay, now there's some things here I'm going to skip because they're conceptual problems, and you might like those, you might not. But here we have a geometric series again. When you look at it this way now, you can see that the ratio is more than 1, divergent. When you look at this one, the ratio is less than 1, convergent. Except here he doesn't want to know just convergent. If it's convergence, find its sum. And the first term is 1. The common ratio is -1/3. So I'm going to have 1 over 1 minus -1/3. I'm going to have 1 over 4/3. 1 over 4/3 is 3/4. So this one, the ratio is less than 1, going to converge. You can find out what to what. This one diverges. You go down here, looks like convergent to something because this looks like a ratio is less than 1. Now, here I have an arithmetic sequence, but I've only got 10 terms. We didn't deal with an arithmetic sequence of an infinite number of terms. All I want you to do is add these up. This is an arithmetic problem. this is an arithmetic problem. It's partial, just so many terms that they want you to do here. And by the way, I think it'd be easier if you change this to 1 minus 0.3 and 3 minus, 2, 4. By the way, is there a pattern here? 0.7, 2.7, 4.7. So it looks like they're doubling or adding 2. It says arithmetic. Arithmetic sequence means you add the same thing to everybody. So they're adding 2. So I just figured that out. So this is that one. This is 2 plus that. This is 2 plus 2 plus, and so on. So when I look at it that way, you can actually, instead of writing this as 0.7 and 2.7 stuff, I could write this as 1 and 3 and 5, maybe. Or I could stay with an arithmetic thing. It is finite. There is a formula for that. So they have 2 or 3 of those in here. Finite sum. And so I'm quiet because I have a phone ringing in my ears. Okay, now, so we have some finite sums there, but here we're back into the series again. Now, what about this? Well, at 11.2, we haven't yet done any comparison test. But could I do a comparison test with this? How big is cosine to the nth power? And the answer is less than 1 or equal. So this term is less than 1 over 3 to the n. If you remember, 1 over 3 to the n is a geometric series that converges. It's bigger terms, and therefore by the comparison test, this will converge. Okay. And since I replaced the cosine of x here by a number, it doesn't matter what the x is, so this is going to converge everywhere. Now, find the sum of the series. Oh, this maybe is a geometric series. Remember, the only kind of series we can find answers for are telescoping or geometric. And so when they tell you find the sum, that's going to be a clue as this is maybe geometric. So maybe I didn't have to do a comparison test. That's good because in 11.2, we don't have the comparison test yet. See, but when you review after you've read the whole chapter, you might try to use a comparison test here, which I just did. But when I read the whole problem, so moral to the story, read the whole problem. Problem says, find the sum of the series. Is this geometric? Well, you fix a value of x. Then I'll have cosine of a fixed number over 3. That's a number less than 1. So the common ratio is less than 1. But when n is 0, what do I get? Now, remember I told you we always try to split this off. When n is 0, cosine of 0 is 1, and 3 to the 0 is 1. So my first term is 1.
Dr. Brady,
Yes.
McKinley let in.
Ah, sorry, somebody wants in. McKinley wants in. Thank you. How'd you know that?
I got good eyes.
Well, you can you I'm glad you got good eyes, but you
No,
guys,
he messaged in the group chat.
can you see who's in the waiting room?
No.
Okay, I just, whenever you
We have a
guys notice
separate
somebody
chat
there,
room.
whenever you notice somebody somehow, tell me because that's so Anyway, McKinley, if you've been out there very long, I'm sorry, I didn't see you. I keep looking, but I didn't see you.
No, I just I had to go take a drug test for an internship, and I just got back.
Ah, well, at least you survived. I had a doctor's appointment this morning and I survived. So, uh, you know, we're both happy about that. What's this? From Grace. Congratulations, McKinley. Yes. Congratulations, McKinley.
About the internship or the drug test?
Whatever. I don't know. Okay. So anyway, maybe we should go to another section instead of number 11, too, you know. So let's go up and see what some of you haven't even thought about yet. And that is, let's go to, I don't know, 11.5 or something and see. In my case, I got to go and look at more things here. So I got lots of them here to play with. If we go to say 11.5, I don't know what that sequence zeros is, but I think I do. And we're going to look at this one for a little while. And I do have something else to do today, but let's just expand this and just see how the problems change. What do they look like? Well, now I know what section I'm in. This is the alternating series section. And that's a pretty easy section. So you guys could go up and do that one, even if you haven't done all the rest of them, because series in the alternating series, they converge as long as the terms go to 0. Okay. And you 1/2, 1/3, 1/4, 1/5 without the minuses, those go to 0. So this is going to converge. And so they tell you this. And so this is an example in the book of how you can deal with alternating series. So you review that, now you're good to go. The second one's going to be similar, except it's got a harder look to it. It says it's alternating, but. Okay, alternating, but. The terms approaching 0, he says, are not satisfied. So you look at this, I have 5n over 7n. Basically, that's going to go to 5/7. That's not 0. Therefore, this diverges. So the two examples there are good because it sets you up for the whole rest of the stuff. Now, in this one, easy to say it converges. He already knows that. He wants you to find the sum, correct the 3 decimal places. How in the world do we do that? Well, this is an example of knowing how far off you are when you stop with any particular number of terms. So if I want to do the first 20 terms, how far off am I? And the answer is the absolute value of the 21st term is an upper bound. So for this example, he wants you to get 3 decimal place accuracy. So he says, okay, I want to add terms until I have less than an error of less than 3 decimal places. And if you look here, if I add these up to 720, the last one, up to 1 over 720. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 or something. Several more. You got them right in here. All right. The next term, or I'm sorry, 1 over 720 is 1 over 504. You probably know that. The next term would be the error if I stop right there. But he's going to stop a little earlier because he says, hey, notice this is 0.0002. So rounded to 6 decimal places, this would work. He wants you to find the sum of 3 decimal places. So certainly if I found it correct at 6 decimal places, I'd be okay. The error of less than this does not affect the 3rd decimal place, so we have that. Well, maybe you could get by with less. Anyway, this is an example in the book about using the error bound to do some computations. Now, this is a pretty simple thing. What's an alternating series? You know, under what conditions does it converge and so on. So this is pretty easy stuff there because you already know that stuff. Test the series for convergence. Is it going to, are the terms going to zero without the minus? The answer is yes, converges. So if you're not that smart, yeah, it shows you how to do that. Again, test the series for convergence. Doesn't look like the terms are going to zero, diverges. Test the series for convergence, converges. Test the series for convergence. It's going to get a little tougher, but not really. It converges because this is a number 1 over 3 plus 8n. Okay, so enough of this section. That's pretty easy. So let's go to section 6 and see what's there. And again, if you guys would talk more and tell me what you really want to do, I could do what you want to do rather than me just playing around here. But section 6. So I'm going to expand this one. What's this about? Well, first, there's 126 points. I only ask you to do 35, 36, whatever it says, 35. So that's pretty easy. Uh-oh, this is a ratio test. Does the ratio test converge if the limit of the absolute value of the n plus first term of n term is less than 1? Yes, that's the ratio test. At least that's one version of the ratio test, the version in the book. Okay. And let's see what the second video is. By the ratio test, this diverges. I don't know, I'd have to check it. That means I'd have to take n plus 1 over 2 to the n plus 1 and divide it by n over 2 to the n and see what I get. And what that amounts to is n plus 1 over n and over 2, but n plus 1 over n and so forth. You have to decide whether that's less than 1 or not. Evidently, it's bigger than 1, and that's why you say, I'm sorry, I just talked myself out of my problem. 1/2 of n plus 1 over n, it goes to 1/2. So that diverges. So when he says the series diverges, you say false because it converges. Okay, well, now we have a whole bunch of ratio tests. So what, or root tests. This one, I would do a root test on. What does that mean? Take the nth root of the nth term. That's easy. You just get this thing inside. Where does this thing inside go? It goes to 3/4. 3/4 is less than 1. Root test converges. So in this sequence of stuff, you're going to have a bunch of things where you test. And okay, what is this? Absolutely, conditionally, or divergent. Okay. Well, if it had all positive terms, convergent and absolutely convergent are the same. Conditionally convergent means the alternating series or the series with some minuses, not necessarily alternating. If it had any minuses in it, it converges, but the absolute value one doesn't. In this case, this is an alternating series. It converges. If the alternating series converges, doesn't mean the original series will converge. But if the original series, or I'm sorry, if the absolute value series converges, then the one with the minuses will. So you got to get those if-thens straight. In this case, why is it absolutely convergent? Because 1 over n cubed, if I get rid of the minus sign, 1 over n cubed plus 1 is a convergent p series with p equals 3, and it's bigger than 1 over n. I mean, 1 over n cubed is bigger than 1 over n plus 1. 1 over n cubed is a p series, converges. So this series converges if I don't have any minuses, and therefore the absolute value series converges, which means this one converges. Now, in this case, this one's alternating, which you can show it converges anyway, but both of them converging means absolute. the sine n over 3 to the n is majorized by 1 over 3 to the n, which is a geometric series that converges. So if I put absolute value around the sine, that's less than or equal to 1 over 3 to the n. So the absolute value series converges, therefore you have absolute conversion. And so this section of stuff has to do with either roots or ratios. Now, sometimes I'll say use the ratio test. That's pretty easy. Okay. And what they do here is they tell you identify this and then write this down and so on. So they're working your way through it. But anyway, this is the ratio and root test section. Now, what I want to do is get out of here for a minute. I want to show you something else, maybe. Let's see if I can go to a different screen. There it is. Okay. I thought I would write down a couple of things here today for you. And this is not it. Okay, this is it here. And that is that there is just okay, that's not what I want to say yet. Okay. The ratio test and the root test we just talked about. If I did this series, now this series is 1/2 plus a third, 1 over 2 squared plus 1 over 3 squared, 1 over 2 to the cube plus 1 over 3 to the cube. It's a little more complicated than the ones that you guys have been looking at or not looking at, but the ones in the book, the ones in WebAssign are not quite this complicated. Now, the root test on this series will converge, but the ratio test is inconclusive. So in other words, if the ratio test works, meaning shows convergence, you got convergence. If the ratio test doesn't show you convergence, in other words, and doesn't show you divergent, and that means the ratio is 1, then it's inconclusive. And if you try the ratio test on this series, it's a little more complicated than the ones you've studied. If you do that, the ratio test doesn't work because you get 1, but the root test might work. So you try the root test when the ratio test is inconclusive. And in this particular case, it works. But we haven't had things like this because it actually, there is a more complicated ratio test and a more complicated root test than the one in the book. And you have to use the more complicated ones to conclude what I just have told you. And what those are has to do with subsequences. Now, if I only look at the odd terms, 1/3, 1/2, 1/2 squared, 1/2 cubed, and so forth, that is a geometric series that converges. If I only look at the even ones, 1/3, 1/3 squared, 1 over 3 cubed, that's a geometric series that converges. Those are two sub-series of the original series, and they go to different places. These geometric go to 1/2 over 1 minus a half, so they go to 1. These go someplace else, okay? Now, any subsequence that converges, I told you one day we have what are called limiting points. The more general ratio test says that if the biggest subsequence goes to something less than 1, then you have convergence. If the smallest subsequence goes to something bigger than 1, you have divergence. And anyway, in this particular situation, the ratio test, when you look at the ratio test, you get different answers depending on which thing you do here. And it turns out that because you get different limits, the more general ratio test doesn't work. On the other hand, the general root test does work. And I just wanted to point out that you can have more complicated series. It turns out there's a root test that's more complicated and a ratio test more complicated. Not going to be on a test, but I thought you might be interested in this series here. This series is 2n factorial over 2 to the 2n times n factorial squared. You don't want to play with this one because none of our tests work on it. But there is a test called Kummer's test, a man named Kummer, a person named Kummer. Kummer's test shows this diverges. If instead of this test, I up the thing a little bit and I do 2n squared, 2n factorial squared, this was just 2n factorial over 2 to the 4n and n factorial to the 4th also diverges. Okay, big deal. This one diverges and this one diverges. But if I do it to the 6th power, it converges. And so these three examples are sort of classic examples of basically your intuition you throw out the window, because you would probably suspect if this one diverges and this one diverges, the next one would diverge, but it doesn't. This one converges. The way to see that has to do with something called Kummer's test. Now, I thought you might like to see two more. If I had a half plus 1 over 3 times 2 over 4, 1 plus times 3 times 5 over 2 times 4 times 6, and so on. So the next one would be 1 times 3 times 5 times 7 over 2 times 4 times 6 times 8, and so on. This kind of series comes up in differential equations, and some of you will be taking differential equations, and you'll have something like this coming up to play with. Our tests will not help you find out whether it converges or not. And for example, the ratio test we were just talking about is inconclusive. The ratio test gives you 2n plus 1 over 2n plus 2, and that ratio goes to 1. And so on this series, you can test it by the ratio test. It doesn't work. You can't very well test it with the root test. None of the tests work, but there's a test called Gauss's test that does work and shows it diverges. And then lastly, I thought you might be interested in the cosine of x over 1, the cosine of 2x over 2, the cosine of 3x over 3. Those all add up. And as long as you don't have x to be a multiple of 2 pi, these converge. Okay, and that brings up a general idea. And it's 24 after, so I should be being told to stop. But so I'm going to stop the recording here. I hope it is.